Hey everyone, and welcome to this Masterclass Explainer. Look, if you're a statistics major or just somebody who loves getting deep into the mathematical weeds of complex survey data, you are in exactly the right place today. We're going to tackle a massive hurdle in statistics, solving the sheer instability of variance estimation in complex samples. It's a tricky problem, but we're going to do a rapid-fire deep dive into resampling and replication methods to figure it out.
Okay, let's dive into this. Here is our roadmap for today. We'll start with the variance estimation problem, unpack the BRR method and its weights, shift over to the Delete-1 Jackknife method, see how that works in complex surveys, and finally, end with a head-to-head showdown between BRR and Jackknife. All right, Section 1, the variance estimation problem. Why do we even need these advanced resampling methods in the first place?
Well, you know standard random group methods. They're super easy to compute, right? But here's the catch. They become dangerously unstable if your complex sample can only be split into a really small number of groups. We absolutely need a better way. Enter resampling methods. And the fundamental aha moment here is in the definition itself. We treat the sample itself as if it were a pseudo-population. By taking different subsamples from this newly imagined population, we can actually use the variability among those subsamples to estimate our overall variance. It's a brilliant workaround. Now, to make this work mathematically, we have to establish a few core assumptions. First up, all the methods we're looking at today assume that your primary sampling units, or PSUs, are sampled with replacement. But wait, what if your PSUs are actually sampled without replacement? Well, you can actually still use these techniques. The math isn't going to break on you. It will overestimate the variance slightly, but in practice, statisticians are totally fine with this because it just results in conservative confidence intervals. Honestly, it's always safer to overstate your uncertainty than to understate it. Ultimately, treating the sample this way completely overcomes the instability of splitting complex samples into tiny little groups. Moving right along to Section 2, Balanced Repeated Replication, or BRR, this is such an elegant mathematical solution. You should know up front, BRR is a highly specialized tool. It has a strict structural restriction. It requires exactly 2 PSUs per stratum. Why 2? Well, 1 PSU simply isn't enough to calculate your within-stratum variance, and exactly 2 gives you the highest possible degree of stratification across the entire population. So, to run BRR, we randomly select one of the observations in each stratum for Group 1, and we just assign the other one to Group 2. This creates what we call our half samples. Now, what's really interesting about this is how we actually choose those half samples. If you have, say, H strata, you mathematically have 2 to the power of H possible half samples. For a big survey, that is way too many to compute. So instead, we use a balanced sample of those possibilities. This relies on something called a Hadamard matrix. It creates these perfectly balanced orthogonal columns of half samples using just ones and negative ones. The 1 means we grab the first unit in that stratum, the negative 1 means we grab the second. The columns are so perfectly balanced that the dot product of any 2 columns is exactly 0. And here is the payoff, the BRR variance estimator formula. Let's read through this dynamically. You've got V hat sub BRR of theta hat, which equals 1 over R, multiplied by the sum of the squared differences between theta hat of alpha r and theta hat. Okay, so what does that mean in plain English? You basically calculate your statistic, say a mean or a ratio, for the full sample. That is your theta hat. Then, you calculate that exact same statistic for just the units in your balanced half sample. That's theta hat of alpha r. You just subtract them, square the difference, sum them all up across all your r replicates, and average them out. It perfectly mirrors the variance you'd get from standard stratified sampling, but it works for highly complex statistics. Let's shift to Section 3, applying BRR replicate weights. Because theory is great, but how do we actually program this into our statistical software? Obviously, we absolutely do not want to literally delete rows of data to make our half samples. That would be a computational nightmare. Instead, we use something called weight shifting. For a given replicate, if an observation unit happens to be in the selected half sample, meaning its alpha value from that matrix was chosen, we just assign it a new replicate weight of exactly 2 times its original weight, 2 times W sub I. If it wasn't selected, its new weight is simply 0. We're just mathematically shifting the weight of the discarded unit straight onto the surviving unit in that stratum. You just pass these new weight columns directly into your software, and boom, it computes the half sample estimates effortlessly. All right, let's transition to Section 4, the Delete-1 Jackknife method. If BRR is a specialized scalpel, the Jackknife method is your heavy-duty, all-purpose statistical multi-tool. See, the jackknife extends the random group method by actually allowing the replicate groups to overlap. Here's the classic delete-1 formula. V hat sub jk of theta hat equals n minus 1 over n multiplied by the sum of theta hat sub j minus theta hat squared. The absolutely crucial thing to notice here is that theta hat sub j is the estimate calculated by omitting exactly one observation, observation j. And look at that multiplier at the front, n minus 1 divided by n. That might look a little weird at first glance, but it is mathematically essential to correct the variance scale. Why? Because your replicates are heavily overlapping by sharing n minus 2 data points every single time.
Now here is a fantastic mathematical aha moment for the jackknife. If you happen to be calculating the mean of a simple random sample, the jackknife variance estimator algebraically simplifies perfectly to s squared over n, literally perfectly. Why? Because the mean, when omitting observation j, is just the full sample mean minus the deviation of observation j scaled by 1 over n minus 1. When you do the algebra and plug that back into the jackknife formula, the sum of those square deviations just becomes your standard sample variance, s squared. The math perfectly matches the standard width replacement estimator. It's beautiful.
Let's actually see it in action. Think back to example 9.7, where we analyzed the ratio of out-of-state to in-state college tuition. To find the jackknife variance of this specific ratio, we strategically drop one observation at a time. So, in replicate 1, we drop the tuition values of 9,912. We completely recalculate the average x, the average y, and we get a brand new ratio of 2.4300. In replicate 2, we put that first observation back in and drop the second one, 7,140. Now we get a new ratio of 2.4555. We do this for the entire dataset, generating ratios that shift just a tiny bit each time.
Once we've collected all those replicate ratios, we plug them straight into our formula. We sum up the square differences from the full sample ratio of 2.425, multiply by our n minus 1 over n factor, and we get our final jackknife variance estimate, 0.05358. We've successfully taken that underlying theory and connected it directly to our statistical output.
Okay, section 5, jackknifing in complex surveys. Simple random samples are great for teaching, but the real world features heavily stratified, multi-stage cluster samples.
If you're dealing with a cluster sample, you absolutely cannot just delete one observation unit at a time. No way. Doing so totally destroys the cluster structure and completely ignores the interclass correlation. The golden rule here is that you must isolate and delete an entire primary sampling unit, or PSU, at a time. And just like we saw with BRR, we use weight shifting again. The deleted PSU observations get a weight of 0. But for the remaining PSUs in that exact same stratum, you multiply their initial weights by n sub h divided by n sub h minus 1.
Take a look at example 9.8 from the text, analyzing Coutts egg volume data. This dataset features 184 clusters in just a single stratum. When we construct replicate 1, we delete PSU 1. Its new weight is 0. But look at PSU 2 right beneath it. Its weight went from 6.5 up to 6.5355. Why did that happen? Because we multiplied it by 184 over 183. We're proportionally redistributing the weight of the deleted cluster across all the survivors to make sure our population totals stay perfectly consistent. So we do this 184 times, let the software run the formulas, and it outputs a highly reliable standard error of 0.061 for the Coutts data. Sure, it's computationally intensive, but this weighting math handles the complex dependency of those clusters flawlessly. Which brings us to our final section. Section 6, BRR versus jackknife methods. And this brilliantly illustrates how we actually choose between these two powerful techniques in the field. Here is the ultimate showdown. Balanced repeated replication is incredibly efficient, but as we know, it's rigidly locked to 2 PSU per stratum designs unless you start using really complex variants. However, its absolute superpower is that it gives highly consistent, reliable variance estimates for quantiles and medians. On the flip side, the Delete-1 Jackknife is beautifully all-purpose. It's flexible for any design with more than 2 PSUs, but it is computationally way heavier. And critically, this is huge, it actually fails to consistently estimate variance on non-smooth functions. Literally, if you need the variance of a median, the Jackknife is going to break down on you. Which leaves us with a fascinating theoretical puzzle to end on. We know these resampling methods are incredible for treating samples as populations, but if the Jackknife breaks down on non-smooth functions like medians, How might missing data, specifically the imputation procedures we use to guess that missing data, further destabilize these variance estimators? It's a massive question that pushes the very limits of modern statistical theory. Thank you so much for joining me on this explainer. I really hope this deep dive into resampling math gives you the structural clarity you need to absolutely crush your next complex survey analysis.